Now next part is electromagnetic induction. Okay, here we are supposed to describe an experiment which shows that changing magnetic field can induce an EMF in a circuit. Okay, now what is the meaning of this first of all? Okay, changing magnetic field can induce an EMF. Whenever you say that in a circuit an EMF is induced, we mean to say that a voltage, that is a potential difference, is created in that circuit. Now how is this magnetic field changed? We'll consider here first of all a solenoid. Let us suppose here this is a coiled wire. Okay, this is being connected to galvanometer. Okay, a galvanometer is a device which simply measures that in which direction whether the current is flowing or not. Let us consider here I'm bringing a simple bar magnet over here. Any pole, say north pole is over here and south pole is over here. I'm just moving this magnet in a particular direction. What is happening is the center zero galvanometer which is there, it's showing a deflection in a particular direction. This deflection will be shown only up to when the magnet is in the state of motion. It means there is relative motion between this magnet and this coiled wire. Of course, this coiled wire is maintaining a closed circuit because here the magnetic field lines, that is the strength of magnetic field lines, are changing. It shows a momentary deflection until the magnet is moving. As soon as the magnet stops moving, the deflection also will become zero. When I'm moving the magnet in the opposite direction, the deflection is shown in the opposite direction of the original deflection which was shown. When I'm moving this magnet continuously in this direction and in this direction, okay, continuously magnetic field lines are changing. Due to this reason, what is happening is, okay, at a particular instant, the galvanometer will show deflection in one direction. Once the magnet has stopped moving, okay, the deflection will come to zero. When the magnet starts moving in the opposite direction, the deflection will be shown in the opposite direction. So when there is relative motion between the magnet and the coil, an EMF is induced in it. Whenever EMF is induced, we mean to say that a voltage, a potential difference is generated. EMF is electromotive force. Okay, there is a slight difference between potential difference and EMF. Okay, but that part will come later. Okay, now here, so when the magnet is moving, there is a closed coil, closed circuit is there. A voltage is generated, it means a current is produced in it. When a magnet is moving in one particular direction, a current will be flowing in one direction. When the magnet moves in opposite direction, the current starts flowing in the opposite direction. If both of these magnet and the coil, they are moving with the same speed in one particular direction, that is the distance between both of these remain constant, at that time no current will be flowing. Because you see, the magnetic field lines which are there, the strength of those magnetic field lines is remaining constant. If both this magnet and the coil with relative to each other, there is no motion between them. It means if they are moving with the same speed in same direction, the relative distance between the magnet and the coil is not changing. At that time, no EMF will be produced, no current will be detected in this galvanometer. Okay. Now this particular effect that is known as electromagnetic induction. It simply states that wherever there is there are magnetic field lines associated with a closed coil, okay, when the magnet is moving with respect to the coil, or even if the coil is moving, there is relative motion between the magnet and the coil. The magnetic field lines that are being cut through this coil, the strength of that magnetic field continuously keeps on changing. That generates an induced means forced EMF. Due to that reason, the current starts flowing through this coil. This is known as electromagnetic induction. Now, what are the factors on which how much is the strength of the current generated in this coil is going to depend upon how many turns are there in the coil. Obviously, more number of turns are there in the coil, greater the strength of current that will be generated. If you are moving the coil at a faster rate, then also more amount of current is generated in the coil.
Even the strength of the magnet.
Yes, that's the third point. Okay, when you are using a stronger magnet, in that case, greater strength of current will be induced into that coil. Okay, so this is the principle on the basis of which we are going to convert mechanical energy to electrical energy.
So the strength of the magnet wouldn't depend on size, right?
No, it does not depend on the size, definitely. So mechanical energy is from motion. We are going to get electricity out of this. Okay, so I'm going to show you the basic circuits of this device, which is going to be known as AC generator. Okay, obviously you know what kind of current is this. It's an alternating current. It means the current is going to flow in one particular direction. It will become maximum, then it will become zero, then it will become maximum in the opposite direction. It means the current is going to flow in the opposite direction. Its value will become maximum. Again it will become zero. Again it will go maximum in the other direction. So continuously the current keeps on changing its direction. Therefore, this kind of the current that we are obtaining, we are going to get an AC current. That is alternating current. It means continuously it keeps on changing direction. The frequency, okay, next term is frequency. It is the number of times the current is changing its direction in both ways per second. Normally the frequency of alternating current, that is AC current, that we are having in our homes is about 50 to 60 hertz. Okay, if it is 50, it means that the current is changing its direction 100 times in 1 second. Okay, so if the frequency is 50 hertz, then 100 times per second the current is going to change its direction. It means it's going to flow in one direction, then the current will become zero, then it's going to flow in the opposite direction, and then again the current is becoming zero. So you see, in one cycle the current is changing its direction 2 times. Okay, so when the frequency is 50 hertz, then 100 times the current is going to change its direction in 1 second. Now this is a simple diagram of an AC generator. Okay, you can see here. Okay, so you can see over here there is a horseshoe magnet. Obviously this is going to be circular, that is curved, concave shaped, so that it gives a strong radial magnetic field. Okay, now this is connected to a center zero galvanometer, and there is a closed coil which will be able to receive current. Alright, now let's take this part. The coil is currently in the position A, B, C, Fleming's right hand rule. Okay, now how this Fleming's right hand rule is going to be there. See, the coil is in this position. I'm going to use my right hand. This thumb which is there, you just write over here father, mother, child. Father is F, that is force. This is the direction in which the motion of the conductor is going to take place. Mother is this finger, okay, that is your first finger, that is the direction of magnetic field. My middle finger or my third finger which is there, this is going to indicate C, that is current. This is the direction of produced induced current. Okay, so father, mother, child. Father is force. This is the direction in which the coil is moving. Now I'm going to apply this particular thing to the coil that is given over here on the screen. Obviously you can see here the north pole is on the left hand side, so my finger is going to come this way. Okay, this is the direction in which the north pole is pointing. Okay, suppose if I am assuming that the coil is rotating in the clockwise direction, If the coil is rotating in the clockwise direction, then my thumb is going to indicate the upward direction. Okay, my middle finger that is coming into the plane of the page. This is the direction of induced current. So the current is flowing from A to B. Okay, this is the direction of induced current. I'm going to show that part once again. This is the direction of my magnetic field that's going from North Pole to South Pole. Okay, this is the direction if I'm considering the part of the coil which is AB. Is going in the clockwise direction, so my thumb is indicating the upward direction. That is the direction in which the coil is moving. Okay, the middle finger that is there, this is pointing the direction of induced current. So here the direction is AB. Similarly, if I'm considering CD part of the circuit, in that case that part of the coil is moving downwards. So obviously that part of the circuit, okay, the current is going to flow in the opposite direction. It is going to come out of the page. Okay, this is going to happen until the coil is reaching its vertical position. Now when the coil reaches its vertical position, at that time the current will become zero. Why? Because here the direction of coil which is there, it is perpendicular to the direction of the magnetic field. The coil has become in the vertical position. Okay, so this is going to be your AB, CD. Here the current is going to become zero. Now because here the motion is continuous, now the coil will still further rotate. Because of that rotational energy, we are going to get electricity out of it, because here rotation is there. Now here obviously you can see the position of the coil is shown over here on the right hand side. Okay, initially when I had considered the direction of flow of current was what? It was from A, B, C, D. Okay, when the coil is in this position, the graph that it is going to show, okay, is going to be this way. When it reaches at the horizontal position, this is the position of the current. This is the magnitude of the current that is shown on one side. When the coil starts moving and coming back to its vertical position, at that time slowly the current is approaching zero. Now when the coil starts moving from here to here, this way, it is already vertical like this. Now it is approaching in the opposite direction to the maximum side. So at that time what is going to happen? The current will increase. It will reverse its direction. In the opposite direction, it will become maximum. That is going to happen when the coil is in this particular position. Now you can see here the direction of flow of current as I apply Fleming's right hand rule. The direction of flow of current is DC to BA. The current has reversed its direction. Again, when it goes in the vertical position, the current from here it is going to become zero. So again, when the coil is vertical, initially the position was ABCD like this. This was when the rotation was 90 degrees. This is when the rotation has become 180 degrees. The current has become maximum. It is at this point. Again, when the rotation becomes 270 degrees, now this is the position. This is how the coil is going to look like if I'm going to see from this side. In this case, AB will be this side, okay, and CD will be this side. Here the rotation has become 270 degrees. Again, when one complete rotation has gone, okay, it has become 360 degrees. Again here, this is going to be the position. So it is going to be maximum again in the original direction, that is AB, CD. This is the entire working of your AC generator. Of course, other parts of AC generator are there. These both parts which are there, they are going to maintain our contact. They are going to be the slip rings. This is your current collecting arrangement which is over here. This is the part where the magnetic field is being caught by the circularly moving coil. If you are going to increase the number of turns over here, then obviously greater amount of current you are going to get. So what are the factors on which how much current will be obtained by this particular AC generator? Of course, the factors that are there. First is obviously how many turns are there in the coil.
Number of turns.
Yes. Okay. Second thing is how fast the rotation of this coil is taking place. And the third factor obviously over here is the strength of your magnet.